Now, next question, I think it's number 8 on the document. You have a cart of mass 35 grams moving at 60 centimeters per second. Now, we're using specific mass units. We're using grams, we're using centimeters per second. So what's the kinetic energy of that mass? Well, we know where kinetic energy comes from, and I think we probably have a pretty good idea where the rule that I said before, where we take 1/2 of the product of the number of mass units by the number of velocity units squared. Where does that come from? It comes from our fourth equation of uniformly accelerated motion. Now there's a calculus connection too, and we'll look at that, but right now, just introducing the idea of energy. We're going to keep it fairly simple as we have so far. And we're going to say the acceleration is net force over mass. We're going to plug that in for acceleration, and we rearrange the equation, and we get F net delta S equals a change in 1/2 mv squared. That'd be 1/2 mvf squared minus 1/2 mv naught squared. So that the work done is equal to the change in kinetic energy. So, our definition of kinetic energy comes from this rearrangement, or from an equivalent development where we integrate the force with respect to position along a path. We can talk about that later. Okay, so the kinetic energy then is going to be 1/2 the mass times the velocity squared. And when we do the arithmetic, I believe this comes out pretty close to 63,000, and the units clearly come out to grams times centimeters squared over seconds squared, meaning that gram centimeter squared over second squared is a unit of energy, because this is a kinetic energy. And this is the unit that you would get from this calculation. So that unit actually has a name. The gram centimeter squared per second squared is called the erg. Okay, it's a unit, quite a small unit of energy. It's kind of interesting when you do calculations of energy produced by stars, which is a huge amount of energy. It's expressed in ergs. I thought that was pretty silly when I first saw it. Why are we expressing that in ergs? The erg is a very tiny unit of energy. Why not megajoules or something like that? Well, we could easily do it. A joule is 10 mega ergs, if you want, 10 million ergs. The reason is that, and it didn't take me too long to think of it. I thought the physics community had lost its mind, but I know it's got a much better mind than I do. So I thought about it for a few minutes, and I realized, okay, yeah, stars produce energy by fusion reactions, by nuclear interactions. And you generally use ergs when you're talking about nuclear interactions. It's a more convenient unit. It's a smaller unit, so the numbers you get for a given interaction are not so huge, are not so small as they would be if you were working in larger units. So there's a certain convenience to using ergs, just like there's a convenience to using grams, centimeters, and seconds in the experiments that we did recently. Those are the units that are most natural. And we're kind of in a no man's land as far as the amount of energy. You see, we're getting tens of thousands of ergs of energy here. And if we were doing it in joules, we would get hundreds and thousands of joules. So we don't really have a good system of units where we can think in terms of simple numbers, say from 1 to 1,000. Still, it's a convenient system to use for the measurements that we're taking. Okay, well, now we ask, what's the current weight? Well, what's weight? We know that weight is the force exerted on a mass by gravity. So we have a mass, 35 gram mass. How much force does gravity exert on it? Well, if we multiply the mass by the acceleration of gravity, we're going to get the force. Now, we could use the acceleration of gravity. We could use 32 feet per second squared. We could use 9.8 meters per second squared, so that we could get the cart weight in gram feet per second squared or in gram meters per second squared. But to keep the units consistent with the grams and centimeters, we're going to use 980 centimeters per second squared. for the acceleration of gravity, so that we're going to get grams centimeter per second squared for the weight of the cart. Okay, so the calculation is very straightforward. We take the 35 grams and multiply by the acceleration of gravity to figure out how much force the Earth's gravity is exerting on it, or how much mutual force the Earth and the cart are exerting on one another. We get 34,000 grams centimeter per second squared. I think that's probably pretty close. The calculations seem to come out pretty simply when I did it in my head, but again, double check me. Okay, and then what do we have? Okay, we have this, and this has to be a force unit since it's a unit of mass times a unit of acceleration. And it's a gram centimeter per second squared. We actually give that unit a name that's called a dyne. Okay, it's much like a Newton. It's 100,000th of a Newton. It's a tiny force. You could feel a dyne of force. Probably not if it is exerted on some parts of your body, but on sensitive parts of your body, you could detect a dyne of force. So we have these units. You don't necessarily have to think right now in terms of ergs and dynes, but you're going to see it, and here's what it means. The general idea is simply, if it's a unit of mass multiplied by a squared unit of velocity, it's an energy unit. If it's a unit of weight multiplied by a unit of acceleration, as here, it's going to be a force unit. Okay, and there are other ways we get it. If it's a unit of force multiplied by a unit of distance, it's going to be a unit of energy. Okay. In any case, we get this frictional force. Now, we're told that the frictional force is 3% of the weight of the object. Okay. Now, that's oversimplifying the way normal forces occur and so forth, but we'll take that oversimplification for now because we're really just trying to get a grasp on the energy situation. Well, that's going to be approximately 1,000 grams centimeter per second squared. Okay, 0.03 times 34,000. Okay, now there's the frictional force, and then we're told that the work done by friction, well, we're asked to calculate the work done by friction. We're asked to calculate how far the object will travel if it has this much energy, this much kinetic energy. How far can we travel on this energy against this frictional force? So the work done by the frictional force is the magnitude of the work done by the frictional force is the magnitude of frictional force times your displacement. And that's going to be 1,000 grams centimeters per second squared, which is the frictional force multiplied by your displacement. And that's going to be your 63,000 grams centimeters squared per second squared, or 63,000 ergs of kinetic energy. So, thinking of the energy accounting, okay, we have 63,000 units of energy. How far can we move against a force of 1,000 units? Well, turns out that we solve the equation easily. We divide both sides by the force, and we get delta S equals 63 centimeters. 63,000 energy units expended at essentially 1,000 force units for every distance unit can take us 63 distance units.